The simplified, high school physics versions of momentum and energy both contain the same notable concept: conservation laws. Conservation laws are invariants, quantities that stay the same as the physics of a system unfolds. So, as systems of objects interact, their total momentum and mechanical energy remain constant. Elastic collisions are the simplest such interaction. In a one-dimensional collision problem, we know the speeds of the objects and their masses, which don't change over the course of the collision. This leaves two unknowns, the final speeds of both objects. Two equations and two unknowns imply that elastic collisions in one dimension have nice, general solutions. This is rarer than it might seem. Even simple-looking systems often behave chaotically and lack closed-form solutions. Anyway, it turns out that most collisions in higher dimensions are secretly just a series of one-dimensional collisions, making their behavior easy to simulate. This isn't true for all collisions, though. In general, momentum is conserved independently in each dimension, which adds more variables. So, conservation of energy and momentum alone don't narrow down the outcomes enough to force a nice solution. In either case, collision problems show how conservation laws can make it easier to figure out how objects behave by placing constraints on their behavior. Constraints narrow down the space of possibilities. Enough constraints compress that space into a single point, a single possibility, a solution. This begs the question, are there more conservation laws we can use? And where do they even come from anyway? In math, a symmetry of an object is a transformation that leaves it looking the same. Some of these transformations are continuous, which means they look like movements that can happen in our physical space. In other words, symmetries are transformations where the appearance of an object being transformed is itself an invariant. So, conservation laws are invariants, and invariants are symmetries, kinda. So, by transitivity, conservation laws should be symmetries too. This is speculation, at best, but it turns out the math backs it up. It's unreasonably effective that way. Conservation laws come from continuous symmetries, not of objects, but of spacetime itself. Physical transformations that leave our empty 3+1 dimensional spacetime looking the same. Spacetime here isn't our universe with all the stuff in it, but rather the geometric description of universes like ours, with 3 spatial dimensions, 1 time dimension, and the same laws of physics. Rotating space leaves it looking the same. So, spacetime has rotational spatial symmetry. Moving it all to the right, or down, or whatever doesn't change anything, so translational spatial symmetry. Finally, the empty, featureless void of space looks the same over time, translational time symmetry. Since each of these transformations leaves spacetime looking the same, by definition, it's like we're just moving the coordinate system around. Noether's theorem associates each of these symmetries with a conservation law. Rotational spatial symmetry implies conservation of angular momentum, translational spatial symmetry implies conservation of linear momentum, and translational time symmetry implies conservation of energy. The specifics of why this happens are, like, a tiny bit beyond the scope of this video and my physics knowledge, but it does. If our universe had more symmetries, we'd see more conservation laws. AP Physics doesn't cover Noether's theorem, but it does cover the 3 conservation laws that Noether's theorem implies. We've already seen conservation of translational momentum and energy. In Unit 6, we'll see conservation of angular momentum and how it constrains the paths of orbiting satellites. Stay tuned for that video at, well, sometime.